Hey, Grace.
Hey, girl.
Hi, Grace. We love you. Grace.
Grace, can you hear us?
Enjoy the next hour.
I'm listening.
Yeah.
So, okay, the
Say no.
definition. Okay. So the definition of the derivative is defined as a limit as h approaches 0 of this quotient here. And this quotient is known as the difference quotient. F of x plus h minus f of x all over h. And the reason that this is, which might help you memorize it, because like I said at the beginning when we first learned this, once you learn the shortcut, a lot of you will probably forget it. So
yeah, that happens.
it happens. So this, we'll say this is this point here on the x-axis, we'll call it x. And we'll call this point here on the x-axis, we'll call this x plus h. And therefore, this would definitely be a distance, strictly in the horizontal sense of distance of h. So if this is x, its output, or the value of the function when we have x, is going to be f of x. And the output here, when we have x plus h as an input, of course, would be f of x plus h. And this is the graph of f. So, how this all works. You guys are more comfortable, at least definitely before starting this topic of the derivative, with how to find slope, right? Difference in y's over the difference in x's. So if I go ahead and I write below this, the limit as h approaches 0 of f of x plus h minus f of x, we would all agree that this is the difference in the y's of these 2 points. Now the difference in the x coordinates of 2 points would be x plus h minus x. Hence, which just simplifies to this.
Wait, why is it that?
It's this because the difference in the x values would be that.
Yeah. Oh. Yep. Got it.
Think of this as essentially dy dx. Instantaneous change in y over instantaneous change in x. Yes?
If the x point happens to be negative, would it just be, like, would you just use the absolute, like, I don't know.
You might be overthinking it, or you might be waking up still because
Does it matter at all?
No, it doesn't matter. So this works for as long as the function is differentiable. And we can touch on that too as a review. As long as it's a differentiable function, this is the formula, right? And then let's recall what makes a function differentiable. Remember, for it to be differentiable, it actually requires more than for it to be integrable. For it to be differentiable, it has to be what? Continuous and what?
Without a cusp or corner.
Yeah, yes, or smooth. So continuous without a cusp or corner, or just to make it more simple, continuous and smooth. So if you have any function that's continuous and smooth, meaning no cusp or corners, you can apply this formula to find the derivative at any point. For any value for the independent variable. So you definitely have to have this memorized. I will definitely ask you to write this one from scratch. Let's think about some other definitions of the derivative. So if I shrink this up and fit it on the same thing here, which I would like to do. So this is one definition. And this is one definition. Let's give 2 more definitions of the derivative. This is the very mathematical definition. Right, with mathematical notation as a limit. But what are some other ways we can describe the limit, the derivative?
Just instantaneous.
Good. Instantaneous. Yes, and that's the third one. Instantaneous rate of change. Can be more specific of a function. Instantaneous rate of change of a function. And then number 3, okay, the slope of, I'll say any tangent line. Now, even though a function may not be considered differentiable for its entire domain, you could still maybe take the derivative of certain points there that are differentiable at those points. Okay, so for example, let's say you had the absolute value function. Right? That's not considered a differentiable function because for its domain, which includes, let's say, at the cusp, that point is that x coordinate is part of the domain. Well, you can't take the derivative of that one, but you could take the derivative at any other point. But at that cusp, that's an issue because the limits would not match of the first derivatives. The rates of change would not match. The instantaneous change would be approached from the left and right, they would not match. Therefore, you cannot take the derivative at that cusp. But we could take the derivative at other parts along the absolute value function because they're just, they're differentiable. They're just lines. Okay. So that's the fine detail that's worth noting, and I'll just write. I know I have it in the notes before, but let's say f of x equals the absolute value of x is continuous but not considered a differentiable function. Because the function is not differentiable for its entire domain. I'll say for its domain. However, f of x equals 1 over x is discontinuous but considered a differentiable function because the function is differentiable for its domain.
Wait, so does 0 not count as part of the domain because there's no function there?
Yeah, so the domain for this function here, f of x equals 1 over x,
Okay, so if there's a
the domain for that function is all real values except 0. And this function is differentiable for the entire domain of this function. 0 is not part of the domain. However, the absolute value function is continuous. We know it is. It's a v. But the issue is that it's not considered a differentiable function because the function is not differentiable for its domain or its entire domain. Because at 0, it's defined. The absolute value of 0 is 0. However, you cannot take the derivative at that point because there's that corner. Yes.
So, sorry, I'm trying to figure out how to ask. The second one is differentiable in its domain.
Yes. Therefore, it's considered a differentiable function. Exactly.
Okay, but what if the absolute value one had a domain of 1 to 5, and that cusp is at 0?
Well, absolute value function is going to have a domain of all reals except one specific value, where that corner is. No matter what.
But she's asking if it's a specific domain, is it continuous? If it doesn't make
Is it differentiable?
Or, yeah.
If they specify a different domain.
But we're just talking about the entire function. It is true, I said earlier, that this guy is differentiable everywhere except at where this corner occurs.
Okay, I guess I don't understand because for the second one, if you were to look at the whole function, it stops somewhere.
No, so this actually, what this guy looks like is this.
Right? Or there's
It is discontinuous
Imagine-
if there's a hole.
There's an asymptote.
There's an asymptote.
Yeah.
Yes.
That's what I was thinking.
There is an
So,
asymptote.
what is that one?
Because it's unremovable.
touch the x-axis, I apologize.
Okay, so 0, if you were to try to differentiate at point 0.
So, this guy is differentiable for its entire domain, because 0 is not part of its domain. 0, let's say the 0 is part of this guy's domain. It's defined. The absolute value of 0 is 0. However, this guy is not defined for zeros, and that's why it's not part of its domain. Right? That's why technically this is considered it's not considered a differentiable function, but this guy is a differentiable function. Fine details here, yes.
Okay, so to be differentiable, a function has to be smooth, but it doesn't have to be.
For a function to be considered differentiable, for a function to be considered differentiable, it needs to be smooth and continuous for its domain. That'll make it even more clear. It's very common to say it the shorthand way that I said it, because when we're talking about just differentiability in general, we're talking about, okay, at some specific point, we're talking about, okay, within that range, it's smooth and continuous at that point, yes, then you can take the derivative at that point. But what I have written up here is exactly right. Alright. Do you guys want to see taking the derivative long way? Like one example, or you want to look at something else?
Well, we have to do it alone.
Oh yeah.
Yeah.
Okay, then
Oh
yeah.
yeah. Okay.
Can we do
Why?
the first and second derivative test as well? How are they gonna make that?
Yes.
Oh, how many questions does this make them want to do?
Why do we have to do this?
Lots of 5 questions at once. Okay, so the midterm is going to be significant length because you have 100 minutes.
Should we expect like 100 questions or like 25
No,
questions?
it won't be 100
Oh,
questions.
a question.
Go, go, go!
And give us help.
So let's see, let's do an example.
That would go with me.
That'd be fun. I'd get through that.
Depending if I have like a mental breakdown.
Let's see, let's make up one that you're expected to do the long way.
So is it not possible the short way, or do they just expect you to do it?
Well, it depends on what I'm going to write.
Like, how are they gonna make me do it the long way?
It's not they're going to make you the long way. They might give you one where they give you a problem that is written as a values are filled in, and you should be able to spot what it is. But they could expect you to do it the long way.
Or if they say.
But it's also good practice, though. It's good fundamental practice to understand how to evaluate
They
limits.
might say, find the derivative.
Because you need to know how to find. Sorry, you need to know how to find. You need to know how to evaluate any limit. So in general, it's a good idea. So
They
anyways,
might tell you.
yeah, I can just make one up. But yeah,
I was like, those might be easier to follow.
let's say one that might. Let's just.
Find the derivative.
I'm not going to give you anything crazier than say some polynomial. So let's say 3x squared minus x plus 1. I'm sorry, what are you going to ask?
They might tell you to find the derivative specifically in terms of limits. Is that right?
That's what we're going to do, yeah.
So they might tell you to do that?
It's possible. I can definitely tell you that I have seen it where they will give you a limit, and if you understand the definition of the derivative, you'll be able to easily see what you're trying to find. Because you say, oh, I see what this is because I know what the difference quotient is. I know what the x is. Oh, I see what they're doing. When we see one, you'll see what I'm talking about. Okay, what we're doing is important. I'm not wasting your time. Okay, so f prime of x is equal to the limit as h approaches 0. Do you guys want to try it on your own first and then see what you get?
Can we do this one together?
Yeah, okay. All right, let's do that. So f of x plus h minus f of x all over h, so it's equal to the limit of f of x plus h. So f of x plus there. So if I plug that in, if I plug x plus h into my independent variable here, I would have 3x plus h squared minus x plus h plus 1 all over h.
Wait, what about the f of x? Minus f of x?
Oh, yeah, sorry.
In the book, they assigned a.
Minus f of x, thank you. 3x squared minus x plus 1. Thank you. Alright, so this part is just f of x plus h, right? If I let x plus h be x, and then subtract f of x. Yes, okay. I would have found that real quick. Wait a second.
Yeah,
Right, so,
are we gonna get 0 or 8?
so here we go. So let's go ahead and do this. So if we go ahead and expand this, the limit of 3, so expanding this is x squared plus 2xh plus h squared minus x minus h plus 1 minus 3x squared plus x minus 1 all over h.
And then we just FOIL it.
And we go to the limit of h approaches 0
Wait,
of this. If I distribute this, is there a question? Did I make a mistake?
do you mind looking over real quick?
Yeah.
Okay, thank you.
If you forget the shortcut, by the way, do it the long way. If you actually write x plus h, x plus h, and do FOIL if you have to.
I'm good if you wanted to move back to where you were.
Thank you. And then notice here, it works out nicely that the 3x squared and negative x squared go to 0, negative x and x go to 0, positive 1 and negative 1 go to 0. So we write out the limit as h approaches 0 of 6xh plus 3h squared all over h. Notice we can factor out.
Minus h2. Minus h1.
Oh, I'm missing something. Oh, thank you. Thank you. All right, so we can factor out an h in the top. So we have h 6x plus 3h minus 1 all over h. Again, this is the limit as h approaches 0. And then h and h simplify to 1 and 1. So we're left with the limit as h approaches 0. This, in a sense, is basically a removable, if you want to think of it like a removal discontinuity, because we're evaluating the limit to what we're approaching. This is why we're allowed to do this. It's fine. So then we have 6x plus 3h minus 1, and then now letting h be 0, you would have 6x minus 1 as time of x.
Okay, can we try one again?
Yes. You would out to
It would have been a whole lot easier to do the shortcut here.
Yeah, again, like I know
I know
that,
it's important.
but you want to say it out loud, so please say it out loud.
Alright, somebody had to.
I'm sure someone will say it again for you.
Most workers never do something special, other than you doubt your basic adding and subtraction because you're used to calculators.
You're going to cause a huge argument if you keep talking.
You don't doubt it, you're adding, what do you do?
One more time. And then at this point, if you wanted to find, say, f prime of 3, now you can just like f prime of 3 would be 6 times 3 minus 1. Plug it in the end.
I don't think, like,
Could you figure it out, what the rate is with that shared I know it'd be super hard, but.
No, you could, it just wouldn't be necessary. It just wouldn't be necessary.
should we make them like normalized stuff?
Do you want any more time? Sorry, was there a question?
Should we make them like normalized stuff?
Yeah, normal lines. Normal lines are perpendicular to tangent lines, and they'll share the same point. So that, since that was brought up, I need that before I continue to bring it up again. So let's say, for example, you have this, and you find the tangent line, say here. The normal line would just be perpendicular to that. It'll share the same point.
Okay.
So you guys know to find the slope of a tangent line using the first derivative. Once you find that, you guys remember the basic fact, don't forget from years ago, that the slope of a line that's perpendicular to another line is going to be the opposite reciprocal. Okay. So yeah, you do need to know both tangent and normal line. I believe that is outlined. I remember seeing that when I was making the outline. So say, for example, you have you guys do, if you have f of x is equal to say 2x squared plus x plus 4, and find f prime of x using a limit. You guys already know that you can check your work, because you already know what you're doing. Yeah, you're gonna find the derivative the old-fashioned way. Raise your hands when I come around and help you if you feel like you're getting stuck on a certain part.
So then I could just do 4x plus 1.
So yeah,
And then I got 4x. And then plus 1, then I got 2x plus 1. Where'd you get plus 1? You're supposed to get 4x plus 1. Yeah, and I got 2x plus 1. I got 4x not the 1. I got 4x plus 4. This is going
You're
well.
supposed to get one.
Oh, because 2 times 2 is 4.
Like I said, that was good. I like that, Rebecca.
I
That was
couldn't
good.
do that better. Because, did you leave the one yeah, we factor out. I'm not too sure.
Did you leave the one and I cancel that? That's why.
H squared,
When you factor out.
okay, never mind.
I don't have it.
Wait, one is there. Oh, yeah, if you take H away from H. Yep, I don't. We go over this.
It's literally.
Yeah, but it's this one, and this H over here. You're factoring out the H. This is
I see where.
I'm taking out the H for each of these, and I instead of I didn't drop the last one, we're gonna pull it out to 1. So it's 4x plus 2 plus 1. So it's 4x plus 2 times 0, which is 0 plus 1, so it's 4.
Never.
However,
Oh, is it however? Oh, I see. However. Thank you.
I came up with it like I did all that, and I didn't catch the fact that I had to put a 1 there, so I pulled out the 8.
And I didn't say.
Don't you love that? You get all the big stuff. And all the little stuff. And that's just something like,
Yeah, exactly.
Yeah.
Did everyone do okay? Your algebra skills? Alright, so you never need to use the second derivative test if you know how to use the first derivative test, right? The analogy I use is that using the second derivative test is like having a machine set on auto. If that machine starts to mess up in auto and you have to switch down to manual, then you can always test the machine work in manual mode. Manual mode is first derivative test. It's a good analogy to think about with that. You can always have that machine work in manual mode, but sometimes auto mode screws up. So you have to go, okay, gotta get it off auto, gotta switch to manual.
Wait.
Wait, what?
That has.
Okay, then throw the analogy out the window. You never need to use the second derivative test if you know how to use the first derivative test. However, it's important to understand how the information used in the second derivative test, or that's part of it, relates to information about the function. Okay, so what does that mean? This is where we're talking about concavity and so forth. And so if you have your textbook in front of you, which I strongly suggest you do, you need to open up to section 4.3.
Which is on 205.
Something. 207. 205.
And go to page 211.
Wow.
Oh, wait.
Great guys. Great job, guys.
And the second derivative test for local extrema in the box theorem 5, it says, the second derivative test for local extrema, if f prime of c equals 0, and f double prime of c is less than 0, then f has a local maximum at x equals c. And if f prime of c equals 0 and f double prime of c is greater than 0, then f has a local minimum at x equals c. So let's say that you're given a problem where the only information you're provided is this information for some specific value c. You should be able to know that it's whether it's a local max or a local min based on what you know about, okay, oh, f prime of c equals 0, what does that mean? Well, that's a local extrema. If f prime of c equals 0, there's a local extrema at c. How do I know whether it's a local max or local min? Well, that goes into account of whether that it's concave up or concave down. And that's what they're talking about when they talk about f double prime c being less than 0 or greater than 0. If f double prime of c is less than 0, that means that at that particular point, that function is at a point where the function has negative concavity or is concave down. Therefore, it would be a local max. And we'll review concavity because I think that's one that kind of slips through the cracks after we don't talk about it for a while. And then if it has positive concavity at that point where f prime of c equals 0, then it's a local minimum. So let me give you, yes?
Sorry.
Should I wait till I'm done explaining? What's the question?
It's about concavity. It's just like a clarification.
That's what I'm about to go
Concavity
into.
is the one that goes like this.
I'm going to explain it for everyone because everyone should.
I thought you were.
You're on my track. So in concavity, let's talk about this. Concavity, okay, that's talking about how the first derivative is changing. You get very, layman's definition of it. How the first derivative is changing. Imagine I take the first derivative or the slopes of the tangent lines. So let's imagine we have a lot of tangent lines. We're going to draw them really sloppily. But I'll do my best.
I really wish you just press a button and hope that the tangent lines would come up.
I am that button. Not bad. Okay, so what do we notice here is that is the slope decreasing or increasing as I draw tangent lines? Slope is increasing. Yeah, -4, 5, -4, -3, -2, -1, 0. And that right there, that O, that's where students were like, oh yeah, it is increasing. Right, because technically -4 is greater than -5, -3 is greater than -4, -1 is greater than -2, 0 is greater than -1. 1/2 is greater than 0, 1 is greater than 1/2, and so forth. So here is the slope, or the first derivative taken at any point, is it constantly increasing or decreasing as we move from left to right? It's constantly increasing. It's always increasing. So this function, which is a quadratic, which has the shape of a parabola, its concavity is always positive, because the slope of the tangent lines is always increasing. It's constant. This will have a constant value for its second derivative. And you can imagine that if you look at it more algebraically, so to speak. If I said, for example, this is f of x equals, I don't know, 3x squared plus 2. Well, what's the first derivative? 6x. And what's the second derivative? Notice, no matter what value I give for a, b, or c, we're talking about that form there, ax squared plus bx plus c. No matter what values I assign for a, b, and c, the second derivative is going to be a constant. Which I want you to make that connection, because look, it's constant. It never changed from increasing to decreasing. This is where it gets, don't let it get fuzzy. This is the rate of change of the rate of change, the second derivative.
Yeah.
On the other side,
Oh, no. It's always increasing. The rate of change, the first derivative, is always increasing. Because remember, the derivative is the slope of a tangent line, right? So let's say the slope of this line is -6, -5, -4, -3, 0, 1, 2, 3, 4, 5, 6. It's always increasing. So this ties into, let me make a connection between that and the second derivative test. So let's say you do the second derivative test, and you don't have the graph though, but I'm showing you the graph to show you how it all ties together. And you know that there's a local extremum at this point because you took that first derivative and you found that the first derivative, when x is 0, f prime of x is 0 when x is 0. But how do you know whether it's a max or a min? Now this one's easy because you learn about concavity, you know about parabolas open up and down, but let's say it's more complicated than that. It's not something as simple as this guy. The reason you know it's a local minimum is because of this right here. Because 6 is greater than 0, this is a local minimum. Yes.
Okay, so say that the graph that you drew is like not there. Okay. And say, what happens if like 6 actually ended up being a max on the graph? Say it was like.
Yeah, let me give you another example to go along with what you're talking about. Anyone need more time on this thing here? So say, for example, it's something more bizarre. So say it's something like 6x cubed. Let's say it's f of x is equal to 6x cubed. And so, okay, f prime of x is equal to 18x squared, and f double prime of x would be equal to 36x. Now, where is this equal to 0? So f prime of x is equal to 0 when x equals 0. Okay, so f double prime of 0 is equal to 0.
I don't understand why you're doing
Oh, this is the second derivative test.
this. Just to find out where the
I'm trying to show you the important piece of
where the
information.
min or max is. Okay.
This is why I wish you didn't walk out the door, because I really wanted you to see if you were just given this and this, or more importantly, what's written in the book. Do you have your book? Okay. On page 211, if f prime of c equals 0 and f double prime of c is less than 0, just based on that information, knowing whether it's a local max or local min.
Yep.
That's the most important aspect I want you to get out of the second derivative test.
What if x double prime does equal 0? What does that mean?
So that means you have to switch to the first derivative.
Oh no! Not going to
Which
overseas.
we're going to focus on now. So let's do that. We'll actually use this.
Wait, so you don't know what the max or min is.
Well, that's what we're going to go over now.
Okay, so the second derivative
you have to
test, the
use the
second
first
derivative
derivative
test
test.
has failed.
So this one doesn't work. You have to use the first derivative.
You have to use the first derivative test.
And it failed because it just equal.
It failed because at the point C, which made f prime of c equal to 0, which is when x is 0, well, f prime double prime of 0 is 0. It's not greater than 0 or less than 0. It is 0. It's failed. So you have to use the first derivative test. And the first derivative test, it says this. Okay, what are our critical points? There's only one. Critical points, where f prime of x is 0, and also where f prime of x does not exist. Okay, so this is where it is equal to, where f prime of x is equal to 0. Okay, so this is the only critical point. Then all you have to do is plug in some values to left and right. So let's say -1 into f prime of x. So f prime of -1 is a positive value. Let's pick the value +1. A positive value. So there are no local extrema
Don't they give you
for f of x equals 6x. You know what this is? This is when it levels out. It's one of those situations where it levels out, and then just it's always it's increasing, levels out, and then increases, but it never decreases. That's what's going on here. Notice how much easier the first derivative test is for finding local extrema. That's why I'm saying this here. All I want you to get from the second derivative test is if you were given just this information before they have the commas here in this box that I want you to look at, that from that you would know whether it's a local max or local min. Yes.
Okay, so back to the 3x squared plus 2, so we got 6 on the second derivative test. What does that tell us? How do we know that it's a min?
Back to what? Back to what?
If it's
Second
for
derivative, 3x squared.
that-
Oh, this.
well,
Okay.
this is zero, it's a max.
It's the opposite of what you want it to be. It's less than 0, it's
And
max,
it's zero.
it's greater than 0,
Yes.
it's 0. It's the opposite of
How do you find critical points again?
Where f prime of x equals 0, and where f prime of x does not exist.
So
Okay,
if
just
it's
say
prime
that.
of x,
So critical points of a function, and this, you can look this up on, all this is exactly what I'm saying. What I'm saying is on Blackboard, but critical points are where f prime of x equals 0, or f prime of x does not exist. Those are the points you need to consider when you're looking to find local extrema using the first derivative test.
and those would be the points that we would put on our
That you're
definition and
testing.
in between. Okay.
Yeah, the critical points, the test points are the ones in between the critical points, and you just pick values in between. You want to see one more of these?
Yes.
Okay.
Can we do one?
Yeah, can we try to do it?
Yes, so let me give you one, let's say, that involves more some other stuff.
Oh, you
Okay,
really need to
so
don't you?
the directions are find all the local extrema. Let's say that's all the directions say, find all local extrema,
You want-
without a calculator.
What is that?
Find all local extrema without a calculator.
This is,
The only thing is, here's the thing, guys. If I let you guys do it on your own, I'm not gonna have time to show you how it's done. So I can do it on my own if you don't want to look up here. You still want to look up here, and I'll do it. You just don't want to look up.
Because I don't remember how to do
Okay.
that.
Quotient rule is actually up on the board from like a while ago.
oh, that's my handwriting.
Okay, so let's just do it together. Again, it's kind of like as you guys are getting older, it's kind of more your responsibility to know to study on your own. So just keep in mind, when you come and see me Monday, the last day to ask questions, you have specific things you want to see. The more specific the problem, the better for you. I want to see number 36 on page this number, Mr. Gross. Okay. Because because you've been studying. Okay. So f prime of x for the quotient rule, derivative of the top is 2x. Leave the bottom alone. Minus, leave the top alone. Times the derivative of the bottom. All over the bottom squared. Two x squared plus 2x minus x squared plus 4 all over. I'm going to leave this guy the way it's written because it's convenient. I'm going to have to shrink it, move a little bit here. 2x squared minus x squared is just x squared plus 2x plus 4 all over x plus 1 squared. This does not look factorable, okay? But let's find out, obviously, where this is going to be undefined. F prime of x will be undefined when x equals -1. Okay, so this is one critical point. Where is f prime of x going to be equal to 0? Well, where the top is 0, as long as, well, even if we repeat it, it doesn't matter. You're gonna be testing this guy. Okay. Now this guy here, unfortunately, I don't think is factorable. I believe it's prime. So we have to use that formula, the quadratic formula. Find your other two. Those are the three critical points you have. Test some points in between. Make sure you plug those test points into the first derivative, not the original. But don't forget, if you actually want to find the value of those extrema, that's when you plug in those points into here and see what their values are.
And it'll tell us to do that.
Don't get that confused.
I've got to put up shoes.